Thank you. It's so nice to have such a big conference about AI in Groningen. I'm very enthusiastic about this, so great. Yeah, so we're going to talk about state-of-the-art transformer pipelines using spacy. And since I realized that, I mean, some of you might be working on language and some of you might be working on image processing. So maybe you're not all familiar with spacy. So we'll first give a sort of broad bird's eye view and then we'll dive in. So spacy is a library for natural language processing. So the idea behind the spacy is you have some raw text, you give them to spacy, and you get back annotated documents. And the annotations that spacy adds are dependent on the configuration of your pipeline. So spacy supports many different components, and we'll show a few of them today. We tailored them a bit to things you probably like the most. So this talk will be very hands-on, so we'll show a lot of code and stuff, so hopefully in the end you have an idea how to use spacy in your own applications. But before we dive into code, I will first give a short introduction to spacy and the typical annotations you can make with spacy. So spacy is a natural language processing library. By the way, I forgot to say, you can simply install it with pip install spacy. And it works largely as a pipeline. So you first run one component and then the next, etc. So we start with text, and in the end we get a doc. That's also a specific type in spacy. It's just called doc. And that is done through a pipeline. So pretty much every component in the pipeline is optional except for the first one. It's always there, which is the tokenizer. So since not everyone may be familiar with tokenizers, I'll give a very brief explanation. So the idea behind the tokenizer is that if you have a text, you have certain words or, say, punctuation signs that are attached to each other, but don't really belong together, say, semantically. So, for example, if you have a word at the end of the sentence, after that you have like the period, which ends the sentence, right? But we don't really consider the period to be part of the last word. That doesn't make sense. We want to interpret it separately. So what tokenization does is it basically splits off the punctuation signs from the words in a smart way. So that's the mandatory thing that's always there. The other components are optional, except probably you want the first component always. And that in spacy, we sometimes call talk to vec. And the name already sort of says what it does. It takes the tokens and produces vectors for them. So there are multiple options here, but for example, you could use a transformer. And the idea behind this is that it embeds the tokens into an embedding space such that similar tokens have similar representations. So the downstream components can use these vectors to do useful stuff with it. So that's sort of the base of a pipeline, and then we can tack on components that we want for the specific annotations that we need. So for example, we could add a named entity recognizer, we could add a document classifier. There are a lot of possibilities there. Okay, so I'll walk through some of them. So first of all, we'll look at it at a basic level, and we can see a doc as containing some text, but not just text, because we always assume that the text is tokenized. So the moment you create, or spacy creates a doc for you, it's going to be tokenized. So we can see it as a container of tokens. So we sort of try to do the tokenization here. Sort of traditionally in NLP, we do tokenization by putting spaces between the tokens, the words and the punctuations, for example. However, that's not really nice because it's a destructive operation. So instead, we keep track of the spans of characters where the tokens are. So here on the slide, to visualize it, we made some alternating colors, which then means that, say here, offer is a separate token from the period here, or the apostrophe S is a separate token from Twitter. So like I said, the doc itself is a container of tokens. So it acts like a list, just like a regular Python list. It is not a list, but it implements the indexing operator to act as a list and an iterator. So you can also iterate over it. So what we can do, for example, once we have tokenized some text, is we can say, well, give me the 9th, counting from 0, token. And so if we do that, we get back an instance of the token class. So the token class is a pretty big class with a lot of properties. So we'll only show a few of them in this talk. And two properties that are sort of the most primitive properties are text and index. So text is the literal text of the token. So if we would say here doc9 text, we would get out the literal text of this token. And the index is the character offset into the raw text. So you can always find back where the tokens were in the text. All right, so now we go to the first sort of real task, which is lemmatization. And lemmatization tries to take words that are inflected and bring them back to their base form. So it's like, if you would, for example, didn't know the meaning of the word accepted, what are you going to do? Well, you look it up in a dictionary, right? But in the dictionary, it's not going to say accepted, it's going to say accept. So lemmatization is bringing back the inflected form to sort of the dictionary form that you would look up in a dictionary. So why do you want to do this? Seems like useless, right? But if you think of it, it has a lot of applications. For example, if you're building a search engine and your text has accepted and your user searches for accept or accepts, then if you do some literal string matching, it's not going to find this instance of the verb to accept. So what you could do is, besides searching on the actual forms, you could also search on the lemmas, and that gives you a lot of higher coverage in user queries, and you would find instances like this as well. I mean, there are other possibilities like computing at a distance or whatever, but this is one way of matching the different inflections of a token. Okay, so the next task we'll briefly talk about is span classification. And span classification, you chop up the text in spans and you try to classify them. So one application where this can be useful is entity recognition. So entities are spans in a text that form some entity, like a person or a company name or a date. So here we have some examples, like in the same text, that Musk is a person, Twitter is an organization, and April 25 is a date. So spans are not just single tokens, they can be multiple tokens as well. So that is why it is a span. So here, April 25 consists of 2 tokens. So you can get these through the doc object as well. So you can say, okay, doc, give me the entities in the document. So this is another property on doc. And we could, for example, get the second entity. And what it returns is a span object. So the span object contains all the information about the span, and in this case, an entity. So we have useful information like the actual text, which might be useful for you if you don't, if some entity is not a single token, but consists of multiple tokens, then you don't have to say, oh, where does the span start and pry out April 25? You can just get April 25 as a single string, which is nice. The label underscore property gives you the label that was assigned to it, such as person. And then there are 2 starting and ending properties. One gives you the offset in terms of tokens. So like start says it's the nth token in the text where the span starts and ends. But you can also get it in terms of character offsets into the raw text. Well, I guess now it's tradition to put cats in a presentation. So we lovingly call span classification in spaCy span cat. So this is the span cat. Okay, so one final task we'll talk about now is document classification, another very common, very useful task, where you just get the whole document and say, spaCy, predict for me the class of this document. Well, the class could be anything, right? It depends on the task you're doing, but for example, it could be sentiment analysis, where document classification says, oh, this is a positive review or a negative review or neutral review. Or it could be something like the genre of text. So here, the genre is newswire. In this case, we have a document, again, and its cat's property is a dictionary. And the keys are the possible labels, and the floating points are their probabilities. So you can see what probability it's assigned to each category. Okay, so now we went through a few possible tasks you can do with spaCy. There are a lot more. But we didn't actually talk about the transformers yet. So this is a very abstract discussion of the transformer and how it's used, but I thought I should say some things about it. So the transformer runs as the very first thing after the tokenizer, and the reason is because we need to get hidden representations for every word, so the vectors for every word. And we do this in a bit of a peculiar way. So what we do is, since a document can actually be very long, and we don't all have OpenAI's hardware, as you might know, a transformer operates in quadratic time, in space, and in speed, right? So if we have this gigantic document and we just run a transformer on it, on the typical GPUs that us mortals have, it will run out of memory. So what we do instead is we break up the text in spans. And typically a span would be something like 128 tokens. Here, to fit it on the slide, we made the span this length, so from station to album. And we let the transformer compute the hidden representations for that. And then the second span, we also compute the hidden representations. Okay, so that by itself might not be very nice because you see that Studio is at the start of the second span, which is kind of bad because it does get representations from its right context, but the left context is ignored as a result of creating the spans, right? So what we do there is we create a span such that there are overlaps between the spans, and we apply some reduction, like taking the mean of the representations or something like that, to compute the representations of these words so that in the end, they represent both the left context and the right context. By the way, all of this is done using a library called Curated Transformers that Madeesh and I made, which supports a lot of transformer models like BERT, but also LLMs. Okay, so once we ran the transformer, we have representations for every word, and then we can apply the different components. So for example, the lemmatizer would just take a representation of a single word and apply a softmax classifier to get a distribution over the classes. In some cases, it's more difficult because SpanCat operates on multiple tokens at the same time. So since each word has its own representation, we somehow have to combine it. So we apply reduction, again, like taking the mean, to get a single representation for the span, and then we apply the SpanCat classifier. Okay, so I'll briefly talk about inference with spacy, and then after that, so here's where the coding starts. After that, Madeesh will discuss training. So the cool thing is that we have many pre-trained models available. So for pretty standard pipelines, you can just download one and use it. And this is done using the spacy download subcommand. So once you've installed spacy, you can use this. So you say spacy download the name of the model. So here, for example, we'll be downloading the English model, trained on web data. And we can then load up the model in spacy by saying, or using the load function from spacy and say we want to load this model. And this gives us a complete pipeline. So now we're going to write a very small web service that just does some inference. We use Fast API to create a single endpoint called annotate. The user provides the data in JSON format. We process the text with this pipeline, and then return tokens, lemmas, and entities. So the endpoint is pretty simple. So we first load up the model, and then we use annotations from Fast API to define an endpoint. And we create a simple function called annotate, which takes a list of strings. So every document is passed or provided as a raw text, so we just take strings. And then we call our pipeline, which has a pipe method, which does then batch processing of the documents that come in. So what we get out are spacy docs. We could return them. Spacy actually has a JSON serialization for that, but they are pretty big because everything like tokens and docs contain a lot of properties. So what we do instead is we make a very small data model and convert the spacy representations to a simpler representation. So for that, we use the convert spacy doc function, which we'll write in a bit. So we use a very simple data model where we return annotations. Each annotation contains a list of tokens, which are the tokens in a particular text, a list of entities in the forms of spans. So the token is just the text and the lemma, and the span is the text, the label of the span, and a tuple containing the starting and ending indexes of the span in terms of tokens. So now we only need to write this function to convert the spacy doc into this very small domain model. Okay, so like I said at the beginning, the doc is just a container, right, of tokens. So in order to pry out the lemmas, what we can do is we can iterate over the doc and we get back spacy tokens. So from each spacy token, we can take the text and we can grab the lemma and we use then our data class and assign it there. Similarly, for entities, we can use the doc.ends property. We can iterate over all the entities and grab then from each entity the text, the label, and the starting and ending position. And then finally, we can create, for this particular document, our annotations object. So here's a small sample run. run the server. We then call curl with a small document, and the output is pretty long, so what I did is I filter using JQ, just the entities, and indeed we get out the entities that are in this text. So now I'll hand it over to Madeesh for training.
Thank you, Daniel. Oh, is this on? Yeah, it is. Lovely. Daniel meant well, but I'm afraid you have to bear with a few more slides of actual theory before we get to the hands-on part. So I hope it's fine with you guys. And let's actually talk about training data. So what do we train our pipeline with? What about some data that's actually from around these parts? So the GMB, or the Groningen Meaning Bank, is an English corpus that's developed by the University of Groningen. It contains over 10,000 English public domain texts that are annotated with a lot of syntactic and semantic features. So among these texts, we have like multiple genres, but it's predominantly a newspaper corpus, which means that most of the text comes from a newspaper. But there's also a smattering of other genres like factoids from almanacs and even stories from the Aesop's fables. And this is particularly interesting to us because we want, by the end of this talk, to actually train a named entity recognizer in our pipeline. So having a number of named entities with training data is good news for us. Besides that, we're also interested in a couple of other annotations, like lemmas. So this is what Daniel spoke of earlier, so dictionary representations of words. And to a lesser extent, part-of-speech tags. These are, well, basically the grammatical category of a word. So is a word a noun or a verb, and so on and so forth. So that's the training data. So how do we configure our pipeline now? So spacy has a sort of structured, centralized way to configure its pipeline. It uses a single file called the pipeline config and contains three major things, well, all of them in fact, the components that you want to train, the settings of the pipeline, and the hyperparameters of the components that you're training. So spacy's components are essentially sort of namespaced plugins that exist in a central repository in spacy's backend. And spacy exposes its built-in components as such plugins, and also third-party libraries can actually plug into this repository system to sort of extend the spacy's ecosystem. And it's the settings of these components that you end up sort of defining in the config file. And this is really good because we only have one file, which makes it a single source of truth, and this makes reproducibility fairly trivial to achieve. So what happens is when you load a config file, the plugins are invoked, and then the different sort of, the components are instantiated based on the settings that are provided in the file. On top of that, we also use Pydantic to perform validation of the settings itself so that you won't inadvertently train a pipeline with a malformed sort of configuration. Let's quickly go over some of this sections in the pipeline configuration. I'll try to speed run this as much as I can. Let's start at the top, and that's the parts section. So the parts section contains parts to like datasets and other assets, but normally you don't want to hard-code them directly into your config. What you rather would like to do is use these as keys and then fill them in later at the time of training. That's followed by the system section. So there's a bunch of settings that are relevant to your system and hardware properties, like seed for your random number generator or your GPU memory allocator policy. And then we come to, I need to do this. There we go. It is interesting. Oh, I'm looking at the wrong slide. Okay, that makes sense. There we go, yeah. So the NLP section is very important because it defines three main parameters of the pipeline, namely the language code associated with it, a list of trainable components, the ones that we plan on training with this pipeline, and the tokenizer that we need to use. This is what Daniel also spoke of earlier. And for each of these trainable components, we need to also describe the different hyperparameters and settings. And that is exactly what you enter in the component section. That's followed by, well, there's this section called Corpora that provides components to iterate over the training data. Batching takes place based on the settings here. And finally, we have the training section as well that contains parameters that are relevant to the training process, like number of epochs to train your model or what kind of learning rate scheduler you want to use. That sounds all well and good, but it's kind of hard to sort of wrap your head around because there are a lot of different settings and whatnot, right? So how do you generate a config? It's fairly straightforward. We have two options. One, you can use the spacy command line command, spacy-init-config. Or you can use, if you're a GUI person, the quick start widget on the Spacy website. It gives you a slightly more interactive experience than the command line itself. But in both cases, you'll get a config that's only partially filled. So the config that you get from in both cases will have some sensible defaults that are explicitly there encoded in the text. But then there are a number of other implicitly defined configuration settings too. And since we want to make our pipelines reproducible, we want to ensure that there are no hidden defaults. So what we want to do there is run the spacy-init, I think this is the one, yeah, the spacy-init fill config command, which will essentially take all these implicitly defined settings and then make them explicit in the config itself. Right, so that's basically training data and the pipeline configuration down pat. We have one final thing, a couple of slides before we can actually get to the code. And this is about workflow management. So, we have a product called, well, it's not a product per se, but it's a library called Spacy Projects. And you can think of that as essentially a make file for ML models. So what it does is, what it represents is an end-to-end way to execute Spacy workflows in a single sort of workflow definition file. It can be used to do a number of sort of tasks. You can use it to acquire assets from a remote server, convert data, train the model itself, of course, package the model artifacts that are found after training, and even deploy that to a remote server or like a REST endpoint. And it has a lot of integrations with existing libraries in the ecosystem, like weights and biases, Huggingface Hub, DVC, what have you. And what does this magical YAML file look like? Well, it kind of looks pretty bad because this resolution is pretty shitty. But ultimately, it's the same as what you saw in the previous pipe configuration. There are different sections here. I'll simply go over the ones that are particularly important. There's a variable section. So this is where the user-facing configuration settings are going to be stored. We have a directory section, just a list of optional directories that need to be created during the course of the workflow. Assets are remote files that you want to download, and then these are corpus files, etc., and then used during your training. And commands are a list of named shell commands that can be executed to actually execute actions. And finally, if you're feeling particularly lazy and don't want to enter all those commands individually, you can define a workflow here, which executes commands in an ordered fashion. Oh, I had all these transitions. Oh dear. Well, onward and upward. So let's actually train a Spacy pipeline with what we know. So we're going to train three main components: the lemmatizer, a named entity recognizer, and a part-of-speech tagger. So this is what the pipeline project directory structure looks like. We have three main files. There's the pipeline configuration itself. There's the script that's going to convert the corpus data into a format that we can consume. And then there is also the actual definition of the project. And the project contains three different commands: corpus, train, and evaluate. We'll just see what they do presently. So the first step is to actually download the corpus. And for that, we run the Spacy project assets command. What this does is it fetches the assets that are described in the project file and then saves them locally. And it can optionally also do some amount of data validation to check it against a checksum that you provided in the file. And once we have the asset file, we go to step 2, which is actually converting the corpus into a form that we can consume. To do this, we run the corpus command that we described in the Spacy project. This executes two subcommands in the background. The first one extracts the annotation files from the zip file we just downloaded. And the second one executes the Python script on these annotation files. The script then converts them into the Spacy-specific format, and it splits them into three different data sets because, well, we actually have to go back to traditional training of models here. So we need a training set, a validation set, and a held-out test set to evaluate the model. That's step 2. Step 3, and you guys probably know the drill by now, you run the train project command. The train project command executes the spacy-train CLI command in the background and takes 3 main arguments. The first one is the path to the actual config file. The second is the path to the training and the development data. And the third is an output directory where you want to save the model once it's trained. This executes the training process, which goes on for a while, depending on how you have your pipeline configured, if you, whether it's going to train for n number of steps or n number of epochs. And it'll also print some statistics to the terminal. So the statistics you see here is the performance of the model on the validation set. And eventually, the training process ends, and then it gets serialized to the output directory that we passed in earlier. Step 4 is when we actually evaluate the model. And yet again, I think I have enough time, so I'm going to repeat myself. We run the spacy project run evaluate command. And this calls the internal spacy evaluate CLI command on the held out data split that we just generated in step 2. This runs the pipeline and the models therein on the test data, and then prints out the metrics that you see here for the different components. So tag here corresponds to the part-of-speech tagger, lemma corresponds to the lemmatizer, and NER corresponds to the named entity recognizer. You may notice that the named entity recognizer is not performing as well as the other two, and you may wonder why. It primarily comes down to sort of 2 reasons. One, we're only training with a specific amount of data, as in we're not training with a lot of data. There are 10,000 documents in the corpus, and for this particular run, I only use half of those. Secondly, we didn't do any sort of hyperparameter tweaking, so that is something that is very much important if you want to eke out the most performance out of your model or your pipeline. And then there's step 5, which doesn't exist because we're done. And what do we do with the trained model? You load it into a spacy like you would with any other pre-trained model that we provide. And how do you do that? Just import spacy, call spacy.load with the path to the model, and you get an NLP object. This NLP object represents the actual pipeline that we trained. And then you can pass raw text to this NLP object using its pipe method, which takes an iterable of text raw strings, and then it'll generate a corresponding doc object, each of which will contain the annotations for that particular text. And you can iterate over the different annotations, as you would have, as you see here, and print out the different entities that we have. So that's about the long and short of training a pipeline with spacy projects and then spacy itself. The example project we just trained, well, I say we just trained, but then I trained it like 3 days ago, and then just put all the screenshots there. But you can definitely do that by downloading it from this particular Git repository. Please feel free to play around with it. You can tinker around, run the same commands that we just saw earlier, or you can go to our website, spacy.io, and just dive into the documentation, figure out what the different sort of advanced features that we offer, and then work from there. So at this point, I give the mic back to Daniël, who will have the last word.
Yeah, so there's also this curated transformers on here, so we wanted to put the spotlight a bit. So this is a library that we developed over the last, I think, year. It started out as, just the old BERT, XLM-RoBERTa and stuff. But over time, we've also added LLMs like Llama 2 and Falcon, etc. And it's a really nice library, I think. So it's nicely abstracted, made of different building blocks, makes it very easy to build your own transformer models with just a few lines of code. I think it was something like 1 A4 of code, and then you could write your own transformer model. So check it out. There's also spacy Curated Transformers, which is linked from this project, which also has another example project how you can train your own pipeline with Curated Transformers. I think that's it. Thank you.
Lucky there. Thanks very much. Great presentation. A couple of questions. We have a few minutes. Going once. Nobody? No, that's it then. In that case,
can I? I was hoping that someone asked, like, oh, but why do this if we have LLMs, right? So we actually added another slide in case someone asked that question. And I think it's worth it, emphasizing that this is something to keep in mind. LLMs are great, right? They're great for generative tasks, but I think like Jean-Paul said earlier, there are also a lot of tasks that you can solve with other models. And what some colleagues of us did was they took some data sets, they wrote prompts to solve the problem with an LLM, and then they also took a training set and started, with 10% of the training data and added more and more, and see at what point the supervised training, the old school of doing NLP, outperforms the LLM on these predictive tasks. And the results are actually pretty interesting. So there are 3 data sets here, and they're all text classification data sets. So you have a text, and you have to give a label to the text. That's the task. And you see that the horizontal lines are the performance of the LLM. I forget which one it is, GPT-3 here. And you see that actually on the most difficult task, the LLM does pretty bad. And even if you would, train on 5% of the training data that's actually available, just fine-tune a transformer model, you already do better than the LLM. And as you train more and more, you get over 90% accuracy, while the LLM is stuck at 70%. And this is similar for the other tasks, right? Like for this particular task, the LLM gets up to 85%. And if we just annotate 1% of the data of the total training set that was available, we already do better. I guess this task. And then we have the final one where you do have to annotate a substantial amount of data. This is another case of named entity recognition, where the LLM, in this case Claude 2, always is stuck at an F-score of 20. And you see that only annotating a very small number of instances, you already start doing better than the LLM. So it is true that LLMs are really great for generative tasks, but it can pay off to annotate just a small amount of data and train a predictive model. And LLMs can help you there, right? So you can write some prompts, let the LLM do the first annotations, and then correct the annotations that the LLM does wrong and train on that. So I think now there's a question. I'm saying controversial things, maybe.
No, I just forgot the question to respond in time. But first of all, thank you, because I've used Spacy a lot of the times, and it avoided me to sort of make pipelines where I had to synchronize tokens and stuff like that. If it's in one place, that sort of magically works. But I was wondering, you spoke about this curious transformer library, and you have this overlapping, like sliding window technique. Wouldn't it make a little bit of sense to cut on the center output, like have separate sentences, use transformers per sentence or per chunk of sentence?
Very, very good question. So this is also quite difficult to answer, I guess. But so there are various aspects here. So first of all, the way sentence splitting is done in Spacy, it actually happens after the transformer, because normally the sentence splitting is done by the dependency parser or a center component if you want to add that. So at that point, we don't have sentence boundaries. One thing that actually happens is, like, as you might know, a transformer splits tokens or sentences or text into pieces, right? So what may actually happen is if you cut these spans, you may be cutting in the middle of a word because a word was split into several pieces. We tried many variations of that, like finding boundaries and cutting on the boundaries. In the end, it doesn't matter at all, weirdly enough.
Oh, empirically, it's proven to not matter.
Right, yeah.
Okay, cool, thanks.
Final question.
So you mentioned also that you have some standard Spacy models available. How do these perform in relation to the large language models?
Mm-hmm. So okay. So the typical Spacy models, it depends a bit on the language, but they are usually trained on newspaper text, and I think we didn't evaluate on that specifically. So we really took these domain-specific data sets and evaluated on that. But I would think that it's going to be similar, right? The thing is just that, if you just want out-of-the-box named entity recognition or something like that, these pre-trained models are fine. But if you're in a very specific domain, where you don't have a lot of data, I think only then comes the question, right? Do I use an LLM because then maybe I don't have to annotate data, or do I train a model, but then I have to do some annotation, right? And I think like if you have an in-domain large training set, it's very hard to beat something like spacy on that. But the question especially arises, like if you were working, I think so, like the previous presentation mentioned text about pensions, right? And probably it's not going to do well on that, these pre-trained pipelines. It's going to do fairly well, but not great, because that's a very specific domain. So then you have to wonder, what do I do now, right? Do I make prompts and let an LLM do it? Or do I create my own data set with annotations? And that's going to take time, and it's going to cost money, right? And I think this is especially when it pays off to use both LLMs and annotations. So let the LLM help you with the first pass of annotating, so that you only have to sort of correct a subset of errors and go from there.
Okay, thank you.
Thank you very much. That wraps up the last talk. So please, a big hand for our speakers.